Okay, so what we're going to do is discuss some concepts that are unique to both steel and concrete design, and really our main purpose for today and for the next maybe 2 lectures, maybe one more, is to discuss what our role is as structural engineers in the design process. Now, you know, a lot of times, students, and particularly this will ring true when we hit, week 3, week 4, we're going to start doing these calculations, and you're going to start asking me questions like, well, wait, do we take the square root of PSI and we get a PSI? What beta 1 value do I use for this concrete strength and what have you? And you're going to get so awash in the details and the specificity of the equations and what have you, that it's really, really easy in a class like this to lose sight of the big picture. What it is that your job as a structural engineer is, okay? And I really want to hammer that in, at least at the very beginning. I know it's really easy to lose sight of this in the weeks to come, so I feel it's my responsibility to at least talk about this stuff here at the very beginning. So let's take an example building, and let's walk through what your job is going to be as a structural engineer. So to start, let me put it like this. Let's take this building, for instance. Let's take the Weisberg Engineering Complex. So how does a project like this go from start to finish? Well, it starts out with there being a defined need. Marshall University says, you know what, we need a new engineering building, right? We need an engineering building on 3rd Avenue to supplement our new engineering program. So Marshall University then contacts an A&E firm or a developer, A&E architecture and engineering firm. And what they do is this A&E firm or these developers, they meet back and forth with with Marshall and the architect and what have you, to try and define the overall scope of what this building represents, what the big picture of the building is going to look like. That's what they do, okay? Then what happens? Well, the architect then says, well, I've got this big picture of the building. Somebody's got to make sure this building stands up. Who do you think makes sure the building stands up? What's that? The structural engineer. That's our job, okay? So that's our job, but there's it's not as simple as that, and there's some points I really want to make about that. So in the world of building design, we tend to work for the architect, but we have a number of tasks. One of those tasks is to maintain the structural strength and safety of the system that we design. And that's pretty straightforward, and that's ultimately what we're going to spend the majority of our semester doing. And the idea behind that is simply this. So you all had me for structural analysis, except for you. Everybody here had me for structural analysis. The purpose of that class was, all in all, to determine the forces on a given structure. You got a beam, got some loads on it. What's the moment look like? What's the shear look like? That was the whole purpose of that class. And you get some maximum moment is 480 foot kips or what have you. Well, that's what you did in structural analysis. In this class, what we're going to do is determine, well, how big does that beam need to be? How much rebar needs to be in that beam such that those loads are safely resisted? That's the purpose of this class, actually sizing and designing those elements. But while we'll spend majority of the semester on that, it behooves us to recognize that that's not our only job, okay? One of the other requirements that we need to meet is this concept of serviceability. It's not really going to make a whole lot of sense now, but it will later when we start talking about deflection limits and what have you. See, let's take this floor system above us. What's above this roof? Beams that are supporting the system, the floors above. Well, those beams, not only do they have to be strong enough to support the loads they're being subjected to, they also have to be stiff enough. The difference being that they can't bend or deflect too much. Now those are two different scenarios. Those are two different questions that need to be answered. And what you might find is that in some instances the beams have really sufficient strength, and what's governing them is the fact that they're deflecting too much. So strength might not even be an issue. So it's definitely something that needs to be mentioned. Also, these concepts of constructability and economy, which are really married together. Okay, let me explain. So let's say, for instance, that this building was a reinforced concrete building. It's not, but let's say it was. Okay, how can I put this in a straightforward scenario? Well, let's think about it like this. How many different beams do you think are in this building? A lot. There's quite a few. I mean, just this floor system above us probably has anywhere from 5 to 6 beams in it. This is one room. How many rooms do you think are in this building? How many floors? It's a lot of stuff, right? Now, if I wanted to, I could be super mathematical, super economical. I'm going to take every single beam and design it to its optimum efficiency, every single one. Now, sounds good, right? There's a problem with that. Okay? If I do that, there is a potential that I have a building with 800 different types of beams in it. Now, in this class, 800 different types of beams means 800 different types of formwork, 800 different types of rebar layouts. Now, go tell a contractor to do that. What are they going to do? Exactly. They're going to look at you like, what? Whereas, wouldn't it make more sense to just design like 4 or 5 beams and just use those same beams throughout? Make sense? That's why, we'll spend a lot of time on the design of a beam, but it's just something I want you to recognize. You might take that beam and use it 500, 600 times in a given building. So make sure that you're doing, not only an economic layout, but a practical one. I mean, do you want a beam to have 6 different types of rebar in it or 2 different types of rebar in it? What's going to be easier for a contractor to build? See what I mean? So it's just something to think about. Now, I asked this question last period. I'll ask you all this. How many of you have heard of Hardy Cross? None of you? All right. You will hear of Hardy Cross at least in 2 avenues around here. If you're involved with ASCE and go to the Virginia's conference, there is a competition called the Hardy Cross competition. Funny how they named it after Hardy Cross. But you will also hear of Hardy Cross because, I mean, he was a very famous engineer, and he came up with 2 very, very powerful tools for engineers. Now, one of them is actually a fluids-related tool. If you ever take, I believe it's hydraulics or hydraulic engineering, and you discuss how water flows in pipe networks, one of the methods used is what's called the Hardy Cross method. And it's very similar to a technique he also developed in structural analysis called moment distribution. So he was a very famous engineer. And one of his sort of key quotes in structural engineering is that strength is essential and otherwise unimportant. And what he means by that is that in this class we are going to get married into the concept of strength, and it's going to be what we talk about all semester. And I just want it made clear at the beginning, that's not the only thing. I mean, there's a whole litany of other issues related to economy, related to constructability, and other issues that, to be honest, sometimes govern. And strength tends to sometimes not matter. So it's just something worth mentioning. All right. Everybody good? Any questions? Okay. So one of the other important avenues that I think is important to mention is what your job's going to be when you get out of here. Specifically, what is your role in a project? How does a structural engineering project go from start to finish? And there's a number of phases that I think need to be discussed, and I want to discuss it in a little bit of detail and see if we can lay out what's going on. So let's go back to my example regarding this building. Okay. Excuse me. So Marshall University says we need an engineering building. So they discuss with an A&E firm and try and get something off the ground. So there's a number of things that need to be done right off the bat. First off, let's have some general definitions in regards to the building. You know, what's the building's purpose? Generally, how's the building going to be laid out? Is there going to be a main atrium with steel stairs that go up from floor to floor and then hallways that spill out on the west and east end of 3rd Avenue? Kind of like this building, you know. How many floors? How many elevators? How many classrooms? How many computer labs? How many faculty offices? Things like that. That type of stuff needs to be sorted out. Now, once you get a general idea of the project and you think, all right, this is going to happen, we're actually going to build something here, now you need to start delineating who's responsible for what, okay? So you need to start laying out schedules and Gantt charts for those of you who've had project management. You need to start laying out what are the fees, how much are you getting paid for this project. Some developers putting a fair amount of money down on the table to build this thing. They need to know what they're paying for, okay? You also need to know the scope of your responsibilities. Where do your responsibilities start and where do they end, okay? How are you going to communicate? Who are you going to ask questions? Are you going to ask the architect questions? Who's going to be responsible to respond to your inquiries? You need to start laying out contracts. Once this is all on paper, are you in agreement? Are you not in agreement? Does that need to be negotiated? That stuff's important and needs to be laid out. All right? Are we good? Now, once that stuff's done, it's time to do some general, what I'll call maybe alternatives design, or you might hear a term 60% design. It's time to start getting a little more into the details. You know, this is a school, so it has certain loads associated with it. You might have, think about it like this. Would it be a fair statement to say that the loads associated with the school are the same as if you were designing a stadium? Are the loads the same? I'd say no. It's a different building. Different building being subjected to different types of loads. All right? Now, here's another way of putting it, if that's a little confusing. This building that we're talking about, the Weisberg Applied Engineering Complex, is in Huntington, West Virginia. Let me ask you this. This building is being subjected to environmental loads like snow. Are we going to get the same snow load here than we are in Anchorage, Alaska? Or in Dallas? What about wind? We're going to get the same wind load here than we are in, say, Myrtle Beach? Hurricane country? No, seriously. If you look at wind speed maps, you'll find that the base wind speed in the country is the same virtually everywhere except for one area, and that's along the coasts. Because along the coasts, you have higher base wind speeds due to hurricanes. Okay, so that's a scenario. What about seismic maps? Are we going to have the same ground accelerations here than we are in, say, Las Vegas or San Francisco? It's not the same story, is it? Those issues matter. Those issues determine what this building's going to look like. Now, how many of you all have had foundations? Anybody in here had foundations? You all are in soils right now? So if you're in soils right now, you're going to be able to tell me all about this at the end of the semester, some geotechnical requirements. And when you take foundations, you'll be able to tell me even more. But ultimately, this building has got to sit on the ground. There has to be some system to hold it up. Now, this particular building is being supported by a series of deep pile foundations. But you'll know what that means from Professor Huffman in the weeks to come. Now, there's going to be some back and forth between maybe you and the architect or the architect and the client. You know, very rarely, very, very rarely does an architect, you know, go to the client, or do you go to the architect and present a solution and they say, good. That hardly ever happens. If I'm spending $50 million on a project, I want it to be what I want it to be. And if our visions are different, you're changing what it looks like because I'm not spending the money otherwise. So there's going to be some back and forth, and there's going to be some iteration. Now, an idea for that is let's say you're dealing with the architect, and the architect comes to you and they say, I want the columns in this building to be spaced 100 feet apart. And I want maybe 4 beams in the whole building because I want wide open spaces for all the usage of the building. Now, if an architect tells you they want all the columns spaced 100 feet apart, what are you going to tell them? You don't think I'm the guy for your job. It's about right. Because structurally, that doesn't make sense. Now, there is a little bit of back and forth, a little bit of give and take, because, you know, at the same time, the columns don't need to be spaced 5 feet apart, do they? So there is a point where the building can not only be optimized for design, but it's got to meet the needs of the client. So there's going to be some back and forth. Once you actually arrive at the hey, here it is, the final design of the building, it's time to do your final structural analysis, the final member optimization, do a takedown of the structure, get all the cost estimates, get the foundations finalized, and now your design is done. Design's done. Is that the end? No, it's never the end. Now it's time to enter the next phase of the project. The design is done. Now it's time to actually build the sucker. And what's the first step in building something? Especially in this world, we got to get ready for the bid, you know? So we got to get all our drawings done, all the construction specs done, get all the bid documents ready, and it's time to go to bid. Now, let me ask you a question. Does the lowest bid always win? No. Why? Well, let me put it to you like this. If I have a project that I think is going to be around $50 million, and somebody says, well, I can do it for $4 million, what do you say to them? Or, you know, BS, right? It's impossible, right? So there's some element of pre-bid meetings and bid review, you know, and there's some, you know, just some general insurance that goes into that. I mean, if you're a developer and you're going to spend $50 million building something, you want some assurance that the folks that you're paying to complete your structure, that they can actually do it. If not, then you're throwing your money away, okay? So that, you know, it's not always the cheapest bid. Now, if it's the difference between 53.5 and 53.7 and it's the same situation, yeah, you're probably going to go with the 53.5. But you know, it's just worth mentioning that, you know, that process needs to be reviewed a little bit. Once you actually get your winning bid, it's time to, you know, complete the structure. You as the structural engineer might need to inspect some things during construction, and then your structure gets built and it's time to move on to the next project. So one thing I'll sort of throw at you is this curve, or these two curves. And there's nothing magical about these curves. It's just something to kind of put everything into perspective when we're talking about these types of issues. So the curve on the left is the ability to influence cost over time. So at the very beginning of the project, when you're in conceptual planning, man, you have a really big influence over the final project at the very beginning, right? At the very beginning, you can decide, well, am I going to do a steel frame or am I going to do a concrete frame? It's a big deal right at the beginning. Also, on the same token, how much does that decision cost? It doesn't cost very much. Now, it sure costs a whole lot to change what the frame looks like once you're already, you know, 12 weeks into construction. That's kind of tough, you know. You don't really have much ability to influence the project at that point. You're sort of done with it. So it's just something to realize that, you know, at the beginning, you have a lot of influence, and it's important to recognize that. Near the end, not so much. Does anybody have any questions just about this stuff in general? Everybody good? Okay. All right. So, you know, before we start getting into things, one of the points I mentioned earlier was that, you know, our goal as structural engineers is to design. What does that mean? How do we design? Okay? How you know, what method, what procedure do we use in general? I'm not talking about the design of a particular, you know, connection or member or element. I'm just talking about in general. How do we approach a design problem? Well, there's a couple of methods about that. But first off, maybe I should just talk about design. Design in and of itself can be defined pretty simply. It's the process of sizing or selecting some member or some component to adequately resist and sustain loads. That's the whole purpose. You have a member that has some resistance to it. It must have enough resistance such that it can adequately and safely resist those loads. That's the long and short of it. So how do we do that? Okay. Now, there's two real philosophies that go into that. One of them is a very simple one, allowable strength design, and one of them is the one we're going to use for this class, LRFD. So, of course, I had to make things complicated on day one. We've got this really simple procedure, and we're not going to use it. I'll explain why. Okay. Now, let's look at the really simple procedure. Okay. So, how do I want to explain the simple procedure? Well, I'm going to use this table. All right. So, here's this table, right? It's a pre-manufactured product. I can go to the store and I can buy this. Okay. Now, here I am sitting on the table, sitting in the middle. I'm three-point bending. Okay. Now, let's say instead of me sitting on this table that this is some actuator in a lab. I've taken this table down to the lab, and I've put a load right here, and I'm pressing on this table, and I'm going to load it until failure, because, of course, any day with controlled demolition is a good day. So I load, and it fails at 800 pounds. I just made that up, 800 pounds. So what I'll call nominal capacity of this table is 800 pounds. In other words, if I physically take this table and put 800 pounds on it, it will break. Okay? Now, let's say that I am the manufacturer of this table. I'm the person that goes out and sells this table to consumers. Am I going to tell people that the maximum capacity of this table is 800 pounds? Probably not from a liability standpoint, because I don't want to tell people that, and then they go and they start sitting and break and they hurt themselves. I'm not going to tell them that. So what I might tell them is instead, now, the maximum capacity is 400 pounds. That's the maximum allowable capacity or design capacity. So what I've done is I've introduced a factor of safety. Now, if this table actually fails, its nominal capacity is 800 pounds, but its allowable capacity is 400 pounds, what's the factor of safety there? 2, right? Okay, so I've incorporated a factor of safety of 2. Okay? Now, that is a reasonable method of design for engineering judgment. Now there's a couple problems with that. All right? Now, if it's your neck on the line, Mr. Hampton, what do you think is a reasonable factor of safety? Is it 2? Is it 3? 2's good? That you can sleep good at night with that. Can you sleep good with 2? See, some people can, some people can't. Some people say, oh, no, 3. That makes me feel better. It depends. There's a little bit of variability on it. It depends on engineering judgment. Now, over time, let's put it like this. If you've designed tables for 20 years, you might go, actually 3 is a little better. We've had some issues with 2 in the past, so 3 might be a little better. So a lot of these factors are based on experience and judgment, which is fine. I mean, if you're designing bridges in some remote village and there's no design code and you just got to go with something, you go with what makes sense. Okay? But there's some problems with that if we want to try and refine our designs. Okay? Now, what I mean by problems with that is that there's a fair amount of uncertainty associated with what we do in design, and just using a factor of safety doesn't incorporate that. Let's go back to my example. How much do we say that this table would fail at? 800 pounds? Now, let's think about this realistically. I take this table. I load it until failure, 800 pounds. What about this table? Isn't this the exact same table? Should it fail at 800 pounds? It should. Is it going to fail at exactly 800.0 pounds? No, there's going to be a little bit of scatter, right? 806, 800. Maybe this one's 792. Maybe this one's 795. While they center around the same numbers, there's some scatter associated with that. There's some scatter for a number of reasons. The material quality. Are you telling me it is the exact same material quality in this table that it is in that table? You can't tell me that with absolute certainty. You can't tell me that the fabrication tolerances are exactly met in every single one of these tables. You can't tell me that, you know. There's also uncertainty associated with the loads. Are you telling me that the wind speed is exact? The seismic ground acceleration is exact? Come on, there's some uncertainty associated with that. And a factor of safety really doesn't exactly take those into account, okay? Now, I know that you all just love probability and statistics. You just wake up and you're, man, it's time for some problem stats. I know it's just, you know, forget Fallout 4 or anything like that, or the new Star Wars movie. It's time to look at some normal distributions. I know things. But the way that we can incorporate or take into account a lot of this stuff is through the use of what I'll call reliability-based methods. Now, let me be clear. I, in no way, shape, or form, expect you to be able to replicate the math you're about to see in these next few slides. I just want you to have seen it and to have been exposed to it so you kind of get the idea of where this stuff is coming from, okay? So what I am getting at is when we do structural design, we tend to look at things from two sides of the equation. We say, we've got the forces, the loads that these structures are being subjected to, you know, dead load, live load, wind, snow, earthquakes, the forces they're being subjected to. And then in response, we have the resistance, how strong those structures are. And so we can take each of those, you know, two variables and look at these as if they're, you know, mapped by some probability function. So you all have heard of a bell curve before, right? Normal distribution. That's just for simplicity's sake. I'm going to assume that each of these two curves, or each of these two components are being mapped by bell curves. So a couple things. Notice how the resistance curve is to the right of the loads. See, I've got this loads right here on the left, and then on the right of that is the resistance, right? What that means is that on average, not, you know, no pun intended, seriously, on average, the resistance is larger than the loads. Is that something we want to happen? Think about it. These are the loads, the forces we're subjecting the structure to, and this is how strong it is. Do we want this over here? Yeah, we want the resistance to be bigger than the loads. On average, yeah. Now, that's one issue. Notice how the resistance curve is taller and skinnier. You'll see that? There's a reason for that. That indicates that the resistance curve has a smaller standard deviation. Now, if you remember from statistics, standard deviations is a measure of how far scattered the data is. A really small standard deviation indicates data that's really close together. A large standard deviation data is really far apart. Wouldn't it make sense that as engineers, we have more control over the strength of a structure than we do with what the user is going to use it for? I mean, does the structural engineer really have that much control over how much load's put in this room? They can, you know, they can design according to what they would expect, but there's more scatter associated with the loads than there are the resistances. Make sense? What we're really after, though, we have a resistance curve, we have a load curve, we're after that. What is the difference between the two? The resistance minus the loads. Now, what I'm actually going to do is stop it here, but I want to indicate a couple things. So what we're really going to try and be after is what's this area right here, this area under the curve. This area is what's going to be called the probability of failure. See, everything to the left of that y-axis is an unsafe system. Everything to the right is a safe system. So if we can control this probability of failure, what it means is we can design structures with a uniform level of safety. In other words, anytime we design a structure, we assure that that structure has the same level of safety as any other system we design. And that's the whole point behind LRFD. Again, I don't expect you to repeat this math. I just want you to have a background in it. Everybody good? All right. That's all I got. You all have a good day, and I will see you all on Wednesday.